Let me thank
Yeah.
Archel, such a nice person to be introduced by. Anyway, thank you very much, Archel. This is a very exciting field, actually, and Australia are definitely world leaders in galactic archaeology, but there's a new field, galactic seismology. It's not started by Australians. This is a field that's been developed over the years in Canada. I think that's my cup of tea coming in. You're a bit late. Sorry. Sorry, it's my fault. So it's my cup of tea. Thank you. I was hoping for my cup of tea before this started. The other field is galactic seismology. That was started by, well, defined, I would say, by Canadians and Americans and so forth. But with the developments in new technology and new satellites and so forth, it's really come a long way. Now, University of Sydney's, well, SIFA is famous for Astro Seismology, Tim Bedding's group, in particular, looking at how stars shake and how you can learn about those stars. We're learning about how galaxies shake and what you can learn about dark matter and the way galaxies respond to perturbations. So both of these fields are areas in which we work, not least because of machines, telescopes, and satellites that we have access to. I'm very indebted, by the way, to the teams I work with, the Galar team. I'm a sort of project scientist for that survey team. The S5, which is people like Grant Lewis, the SAMI team led by people like Scott Groom and Julia Bryant and Jesse von der Sonde, Nick Scott, and the Hector teams, which is a follow-on from SAMI. I'm even more indebted to 4 research fellows. I've worked with many more than these 4, but the 4 that I work with at the present time, Sanjeev Sharma, Torsten Tepe-Garcia, Jesse von der Sonde, and Michael Hayden. I've learned so much from them. They've been research fellows working with me over the last 5 or 6 years. And much of what I'm showing of someone in that list has done as much or more than I have to make this come to fruition. So it's a very international field. Nowadays, you can't do big things without involving yourself with large teams across the country, and of course, teams from overseas as well. So I have lots of international colleagues, which is why I used to travel a lot, and not so much at the moment. So there's a punchline here. Stars provide us with a look-back time of at least 13 billion years to processes in the early galaxy, and this is the foundation of galactic archaeology. You've probably seen a picture like this in your lectures, or you've probably seen it in a popular magazine. Big Bang is over here, and cosmic time is passing over 13 or 14 billion years, and it goes through these various transitions of fog of hydrogen, dark matter taking over, and gas collapsing into dark matter then collapsing with the gas to form stars, galaxies forming, and quasars, black holes growing, and so forth to modern day galaxies. So that's one approach. You can look back in time with satellites, look all the way back through cosmic time by observing very, very faint with powerful telescopes like the Hubble Space Telescope, Keck Telescope, or the ESO VLT telescopes. And you can look at fainter and fainter things and learn about the evolution of the universe. An entirely complementary approach is to look at stars in our own galaxy, like analyzing the Milky Way. Also, some work, you can extend this definition to M31, Andromeda, the local group of galaxies. But primarily what my concern is studying the Milky Way, because you're always going to have more information, well, more about stars than in the Milky Way than you'll ever get from any external galaxy. So this is essentially a different approach from far field cosmology. So we often refer to this as near field cosmology, because we find stars which trace all the way back through cosmic time. So some stars are thought to be at least 13 billion years old. So the field started, some form of galactic archaeology has been going on for a very long time. Nancy Grace Roman in the 1950s, she talked about stars moving in strange ways and having strange stellar abundances, metallicity, and that was essentially her discovery. And you might say that the field started back in the 50s. But since the 1980s and 90s, Ken Freeman and I were looking at ways in which we could describe the field more systematically. And this led to the general field of galactic archaeology and near-field cosmology. And I make that point in the abstract, as you can see here. This is from 2002. basically that there are distinctions. Looking at the galaxy, we'd call this near field cosmology. Looking at the very high redshift universe, we'd call that far field cosmology. And this field has taken off in many ways. A lot of instruments are devoted to this field, and there are a lot of future instruments and projects being devoted to the field of galactic archaeology. The main themes that this field I've looked at within this field is, how did the galaxy form and evolve? How did the dwarf galaxies form? These are thought to be very ancient. There's about a few hundred in orbit around the Milky Way. There may be many more that we haven't yet found. Simulations suggest there could be as many as 1,000 dwarf galaxies, depending on how you work with those simulations. Maybe it's less, but we definitely see something like 50 to 100, if you include all the disrupted streams around the Milky Way. Also, how did the elements form? You know, the universe began with hydrogen and helium, and then in time we were able to form carbon, nitrogen, oxygen, silicon, sulfur, and beyond. So the element table we have today is a snapshot in time of complex processes that have taken billions of years to get us to where we are today. Where did those elements come from? And we think that different sources, different kinds of celestial objects at different epochs have created these elements. So we can look at these elements in stars and try to infer at what point and what kind of object gave rise to the elements in that star. An interesting question which is relevant to this is, where are the oldest stars today? We see young stars, we see moderately old stars, and very old stars, and very ancient stars. There are certainly strong clues that some stars are truly ancient, like radioactive decay in their abundances, and other inferences about how elements fell into their first black holes. So there are a lot of experts in the field who'd say that some of the stars we're looking at are literally, would have formed at redshifts of 7, 8, 9, 10, or even earlier. So, but the question then becomes, where would you look? That's not at all clear. Do you look at the dwarf galaxies? Do you look at the center of the galaxy? Do you look at the halo? It's hard work to look for the most ancient stars that give you the earliest signatures of the universe. So this issue of galactic seismology gets to the issue of what is the nature of dark matter. You know, can you detect that dark matter is just gravitational in the normal sense, or is there something much more strange going on, like Celine will tell you about bosonic matter? There are some very interesting ideas. In fact, Archel as well knows about interesting variants on what dark matter might be. Another very interesting topic, which is I think future-proofs astrophysics, is the black hole, the galactic center, the supermassive black hole called Sagittarius star. That's a really odd creature. It's been probably the oldest thing in the galaxy, along with some of its surrounding dark matter. These are thought to form around from the first stars, and they grow at different efficiencies. The one in Andromeda, for example, is 50 times more massive. So Andromeda and Milky Way are about the same mass. 1.3 or 4 times 10 to the 12. And the black holes, though, in M31, the black hole is about 10 to the 8. In our galaxy, it's a few million times the mass of the sun. So it's quite strange that these two galaxies, which are so similar in so many ways, not in all ways, of course, have black holes which are completely different in their mass. So what is the nature of our black hole? And in fact, there are many experiments focused on understanding the activity surrounding the black hole and the black hole itself. And a parallel theme, which has been a feature of my own work, is how does gas enter into galaxies? Because this gas is what feeds and grows black holes. It's what feeds and grows stars and the different components of the galaxy. These are all formed through gas. You don't form them out of dark matter, as far as we know. They form through gas. But how gas gets into a galaxy early on and much later, like now, today is what you see today is a real mystery and very difficult to explain because of the complexity of hydrodynamics and gas physics and cooling and so forth. All right, so I won't say much about chemistry of stars at all. I have written a number of papers in this field. There's a review you can read at your own leisure in 2013 with 2 of my colleagues, Volker Brum and Tortny Carlson. Tortny was actually in University of Sydney with me. And we looked at the models that were being produced, for example, in Japan, to see if we could infer something about the nature of the first stars from the abundances of stars that you observe today. It's a very, very difficult, ongoing, difficult problem, but a beautiful problem to be involved in. It gets you into supercomputer simulations and observations with the most powerful telescopes. More recently, there's another review you can read. This is 2016. I've tried to update the field of galactic archaeology at some level by giving a summary of the main parameters and ideas that we have for the Milky Way. And it basically shows you how far we've come. And there's a great deal that we do know about the galaxy, but they also outline many things that we know nothing about whatsoever, not least the nature of dark matter. Okay, so astronomers project the Milky Way onto the sky, and we normally work in a sort of a flat plane when we present things on the sky, and that basically comes from us here at the sun at a radius of about 8 kiloparsecs. It's about 28,000 light years from the galactic center, and we project things all around us onto a 2D plane. That's what you're probably used to seeing. Nowadays, though, we are far beyond that. We're not only do we have three-dimensional positions for stars, for not all stars, but some useful fraction of stars, we also have three-dimensional velocities. We can tell how many stars are moving in 3D space. So if you take this artist's impression of the Milky Way and project that onto the sky, you get this. This is looking in the mid-infrared where you're not bothered by dust, and you're just counting stars in all directions and projecting it onto this plane. And already by doing this, using the WISE infrared satellite, you get this beautiful projection, if you will, of the Milky Way. We're living within that Milky Way, so we can't see it from outside, never will. But what you do see from projecting is Sagittarius, constellation. You see the bulge of stars from the galactic center. It's like downtown Sydney, if you will, where stars pile up. Then you have this very, very thin plane. The inner plane of our galaxy is very, very flat and very, very thin. Going further out, that plane becomes rather more complicated, as you'll see. There's also a bulge of stars that extends further out, a stellar halo which goes even further out. There's a thin disk, and there's a thick disk of stars that's a little bit difficult to detect in this particular image. So half of those stars, quite surprisingly, formed before a redshift of 1. It's people often imagine that the old stars are a small fraction of the Milky Way or modern day galaxies because they look so blue and they're full of young stars, but those young stars dominate the light, but the actual mass budget is dominated by old stars. And that's true of all galaxies, even the ones with lots of young stars. You'll find the presence of a large fraction of old stars. And the old components in our galaxy include the dark halo, stellar halo, the bulge in the bar, the thick disk, and the old thin disk. When you add up how much mass we have in all of these, it adds up to about half the mass of the Milky Way. So this is all consistent with the idea of galactic archaeology, looking at the oldest stars to unravel how the galaxy was born and how it evolved. So that's the sort of talk I would have given 20 years ago when we wrote the review, but things have moved a long way since then. And the big revolution has come from new machines, new satellites, new ground-based telescopes that can measure positions and motions of stars, distances, and also other properties like masses and ages and so forth, to much higher accuracy. And this has been a revolution, as I'll show. So we call this field astrometry, measuring the positions of stars. And this goes way back to Edmund Halley. In his time, we talked about proper motions. Proper really means a star, the properties that a star owns. It's not really proper as in correct motion, which I used to think. It means the own motion of a star, the French word prop. And this proper motion is language. It's become the anglicized now to P-R-O-P-E-R, but it originally began with the French spelling. And somewhat later, James Bradley discovered that stars really do move. I don't just mean from the rotation of the Earth. I mean they physically move their positions. Notation I won't get into now is to do with the rotation of the Earth's axis and so forth. And in fact, Freeman Dyson says that James Bradley, when he was quoting measurements of positions to 4 significant figures, this was the beginnings of modern science. This is a comment that is often in Freeman Dyson's writings. So accurate measurement and consistent, repeatable measurement was the beginning of modern science, which is interesting that should be associated with astronomy. Much later, 100 years later, Friedrich Bessel discovered the parallax. This is the fact that as the Earth goes around the sun, we physically see stars move on the sky. That movement is real if they're close enough, much like when you look at your finger and blink left and right with your eyes, you see the background shift with respect to your perspective. And in fact, if you're looking with a satellite and measuring positions over a long period of time, you would see this. You'd see essentially a star tracking across the sky if it's close enough to us. And on top of that, you would see this rather beautiful curlicue motion due to parallax. That's the Earth's motion around the sun. And on top of that, you can, for some stars, even see another epicycle on top of this due to the presence of planets pulling at the star as the star moves through the heavens. So astrometry, it really has been a revolution for how we perceive the heavens, because we can do this now accurately for millions of stars. So near-field cosmology builds the whole concept of astronomy into it, astrometry into it, the notion of a parsec, which is the parallax of 1 second of arc. This is how we measure distances. So that would be a star, one of the nearest stars to us, like the Proxima Centauri, Alpha Centauri, that would be about a parsec or so away, and that's pretty close beyond the sun. And that's built into the whole notion of measuring distance. And there have been a number of extraordinary breakthroughs. I won't have time to go through any of these, except very briefly. One is VLBA, the idea of combining radio telescopes for accuracy of positions. So for the Galactic Center, for example, we can detect with astonishing accuracy that because of masers and sources in the Galactic Center, how we move with respect to the Galactic Center. So we know to better than 1% accuracy what our speed of angular velocity is with respect to the Galactic Center. And then there's this wonderful project in Chile. The Europeans have combined their 4 telescopes to build a machine called Gravity, and that measures movement of stars with astonishing accuracy, normally focused on a target like the Galactic Center. I'll mention that in a moment. And then the next one, which has been the most revolutionary technology for galactic archaeology, has been Gaia, the ESA, European Space Agency Gaia mission, which measures the 6-dimensional phase space of millions, possibly billions of stars. So first of all, gravity. Gravity is very important to galactic archaeology because the most important number to us, would you believe, if you really want to get your models straight, if you really want to understand what's going on, you need to know your distance from the galactic center to very high accuracy. So we have our angular velocity from VLBA, but we also want to know our actual distance. And these are very separate measurements. So ESA gravity is an astonishing experiment which builds on tremendous developments at University of Sydney. And they openly acknowledge this. A number of smaller experiments around the world which revolutionized astrometry. So SUSY, that was Sydney University Stellar Interferometer out at Narrabri, and that's all closed down now, but people like Peter Tuthill was involved in that. And we've had a number of John Davis, John O'Byrne, I can't even remember now the people involved in that experiment, but it was a lot of those ideas, successful demonstrations were built into this amazing project at ESA VLT. So it really is the living embodiment of a radio telescope in the optical. They do phase referencing on a source, a bright source in the field. It's actually harder than radio interferometry because they've got to do it in real time. You can't do it post facto. You have to do it essentially in real time at 1 kilohertz because of all sorts of rapid variations going on in the system and in the atmosphere. And what they've done in particular is measure the one particular star with astonishing precision. They've measured a star, how it's moving with respect to the background stars, which is a difficult thing to get straight. But what you do see is day by day, in principle at least, at the peak of its motion, you see one of these stars reach something like 8,000 kilometers per second. That's 40 times faster than our sun's moving through the galaxy as it goes past the central black hole. It really is incredible what they've achieved with this gravity machine. And what that did, so the Newtonian measurement would be the gray line, and the prediction from post-Newtonian, this is the GR result, Einstein's general theory of relativity, is this here, which they detect at something like 12 sigma. So they have a beautiful, so you're literally seeing the effect of general relativity on the orbit of this star as it goes past the black hole. And as you can imagine, having that level of accuracy means you also get a very accurate position for the galactic center because of secular acceleration and so forth. So here are their measurements, 8.178 kiloparsecs plus minus 0.025. we gave a number a few years earlier, which was somewhat consistent. I mean, we're excluded by their error bar, but they're within our error bar, as it were. The black hole mass, now known to 4 significant figures, possibly, or 3 significant figures. 4.15, 10 to the 6 solar masses. So it's basically 4 million times the mass of the sun. And the circular velocity, that comes from combining it with the radio measurement from radio phase reference astrometry. So anyway, you can see now that we have the era of accuracy of measurement or precision measurement in astrophysics is upon us. It's certainly not the case that we can do everything in the same way. There are certain measurements we do extremely well, and a lot of other measurements that we do relatively well, but nothing like as good as this. So the impact of the satellites, like ESA Gaia, NASA Kepler, which is more in Tim Bedding's field, looking at how stars flicker, the NASA TESS mission and other missions have really revolutionized the way in which we perceive stars in the night sky. So let me just pause for a moment and grab a cup of tea. My cup of tea. So one of the things we want to do is to build dynamical models of the galaxy. This is important because what we want to understand is the galaxy an equilibrium figure. Everything you see when you put it together, say in a supercomputer simulation, the kind of work that Torsten Tepe-Garcia does, or used to do when he was a research fellow in this particular area. When you build these things together and make them run, do they fall apart or are they sustained by their own gravity? So that's something which we're trying to do because we want to understand if the Milky Way is an equilibrium figure, or in fact if it's sort of undergoing some kind of strong non-equilibrium evolution because of interaction with its own dark matter or with infalling galaxies. So the way that you do that, now that we have these 3-dimensional velocities and positions, we have a Vz, which is up, down. With respect to the plane, we have V phi, which is the motion around the plane, and then we have V radial, Vr. We can do it in terms of the velocities. We can also do it in terms of action angle variables. So what we're after, it says here, we're after a potential and a density distribution that support each other. You want the potential which controls the orbits through forces, the gradient of the potential, and the density distribution that you're inferring in your model. You want those to go together when you rebuild them and be self-sustaining, and that's very, very difficult. This has been going on for almost 100 years in astronomy, and I'd say we're a lot further along, but we still don't have a sort of a final solution. We're sort of always working with perturbations of these models. So the action space, or the angle action space, is very important because we've got such good information now on stellar motions. We actually are able to look at how these things oscillate up and down like this, how they oscillate in and out. This is the radial direction, and in fact the nature of the angular momentum properties as well as you go around the orbit. All stars precess. There are very few stars. Only the youngest stars have circular orbits, but within a very short time they scatter and go into elliptic orbits, precessing orbits as well. So essentially all stars have these precessing orbits. And from these Hamiltonian, action equations, it's relatively easy to derive the Hamiltonians and work with those as well. Okay, so here are some of the new data. I would say these are data that were unthinkable to me as a graduate student. It was even possible to do this. It's astonishing. So this is V phi. Just go back a second and remind you that V phi is the tangential motion. So if it was a circular orbit, it would all be V phi, and there'd be Vz would be 0, Vr would be 0. So V phi is like V tangential. It's the circular. It's the component of motion in the tangential direction. So here's a beautiful figure that was taken from the ESA Gaia satellite. So you're familiar with the idea of a flat rotation curve if it was gas in rotation. And that would start down here, a radius of about 0 kiloparsecs. It would rise, then it would reach a plateau, and then it would go somewhat flat all the way out to the edge of the galaxy like that. So that's what gas would do because it dissipates when it interacts with itself. But stars are different. Stars can do anything you like. You know, they can undergo lots of complex elliptic orbits. They can oscillate above and below the plane. They can oscillate in and out, like epicycles, like the ancient Greeks knew about. And as a result, you don't just get stars all moving in circular rotation, which would be along that plateau like that. That's what the gas does. Stars don't. Every single dot in here is an average over thousands of stars. So a star down here, for example, would be rotating way below the circular orbit motion velocity up there. So what that star is doing is presumably doing something like going around highly elliptic like this. Can you see my cursor? And processing at the same time, like that. So essentially, every single dot in here is an average over stars performing really complex orbits. Now, the reason you see it all pile up at 8 kiloparsecs is because these are real data. These have not been corrected. And you're seeing the pile up because we see many more stars near us at 8 kiloparsecs than we do further away. Now, on top of this, so obviously, you know, if you're observing stars to some brightness limit, it means that at some points, star counts fade away because the further away you go, they just get fainter and fainter. So on top of, so you've got basically a maximum of stars near us, and they fade away slowly as you go further and further away, because there are fewer and fewer stars being picked up within this magnitude limited survey. This will look a lot better when the next release. This is just a release from 2018. Now, if you look carefully, you'll see these ridge lines going through the data, these diagonal ridge lines. These were completely unexpected. There was no model predicting these things. There was no one saying these should exist. I mean, there were theorists saying that you can get things like resonances, but they weren't observed, they weren't inferred or observed in previous surveys, which is rather wonderful. So we've had a PhD student, Shurya Khanna, who finished maybe last year, and he went to the Netherlands for his postdoc. And Shurya worked with Sanjeev Sharma in particular, and with the University of Sydney group to understand what were causing these ridge lines. And that in itself is a very, very interesting problem. Now, if you project the data somewhat differently, not just v phi as in this tangential component, but also vr as in radius. So it's an inward-outward motion and the tangential motion, and go into that plane. VR of 0 would be circular orbit, and then v phi, that's our circular speed at 240, about here somewhere. What was really surprising was to find that all these stars clump. It's not just a uniform Gaussian cloud, like a sort of a hot gas would be Gaussian distribution of, like Maxwellian distribution of particles going in all directions. In fact, it's clumpy. It doesn't look like a Gaussian cloud whatsoever. And these individual clumps, each clump here is telling you something about how stars are piling up in resonances, or maybe because of the effects of dynamical perturbations when the galaxy was hit, or conceivably the interaction of dark matter with the Milky Way itself. So that all of these clumps that you see in this projection have their own story, and each clump has to be sorted out essentially. You have to figure out what these stars are. Are they all the same age? Are they different stars? Where are they in the sky? Are they in the plane? And so on and so forth. So this was already a great revelation. There were intimations of clumping. Hello? Was there a question? There were intimations of clumping in the past, but nothing like you see here with such high contrast. The next revelation, I think, which for me was the most exciting, one that we're working on a great deal at the moment, is this one. This is not VR nor V phi, this is purely VZ. So remember that VZ was the up and down motion. So if you plot for millions of stars, VZ versus Z, so that's the Z is the height above and below the plane, measured against VZ, the motion above and below the plane. So think of a harmonic oscillator, for example, going backwards and forwards. VZ and Z, if that was your harmonic oscillator swinging backwards and forwards, and Z was that distance, and VZ was the velocity, they're out of phase, where V is maximum going through the middle, Z is 0. When VZ is 0 and Z is maximum, so they're out of sync because it's a simple harmonic oscillator. So if it was a star which was doing purely simple harmonic motion above and below the plane, and all the stars were doing that, they'd all form circles, a perfect circle in the Z and VZ space. But that's not what's seen by the Gaia satellite. What they see is astonishing. I don't think anyone expected this. What you see are stars not in a circle, but in a spiral. And that spiral goes all the way in like this. So the way to think of that is somewhat difficult, and I'm going to have to summarize it very quickly so I can move on. Is imagine you have sand grains bouncing on a drum skin, and the sand grains are bouncing up and down, and they're all performing their own harmonic motion. If they all had different amplitudes, you'd have a whole bunch of circles, concentric circles in here. Now imagine that you hit that drum skin, and then essentially the drum skin starts doing this, and as the drum skin comes back up, it forces all these random motions into, or at least the stars that get interacted with, into some specific periods. And then the periods, then those stars which have been pushed into specific harmonic frequencies are then settling down, what we call phase mixing. So what this is, and it would take me quite a while of showing you all this new work, which I won't have time for. You'll see that soon, I hope, when we give a seminar on this. What this is telling you is that there is, in fact, that the galaxy disk itself has been punched very, very hard by one strong impulse. A very massive object, something we haven't yet seen, or one of the dwarf galaxies that we see now, has punched through the disk very impulsively. And that disk essentially got rattled, and it's been trying to settle down over hundreds of millions of years. So that was, again, unexpected. And I think this single beautiful figure from Teresa Antoja's paper, her now famous paper in 2018, has essentially given rise to what I would say is real-life galactic seismology, because a lot of people are trying to understand what these resonances are telling us about the structure of the galaxy, what you can say about dark matter models, and so forth. All right, so there's also been a revolution in how we measure stellar abundances and stellar masses. I will focus on what the Australians are doing, but there are similar projects, much of it inspired by Australian work, I should say, going on around the world. If you look at the spectrum of the sun, you're all familiar with the idea of the sun's light going through a prism and seeing a beautiful rainbow, or through raindrops and seeing a rainbow. But in fact, if you took that rainbow and magnified it, stretched it by a very large factor, and you had very good sensitivity, and you had a nice spectrograph that gave you very high quality spectra, you would find 25,000 absorption lines in principle, if you have high enough magnification. So this is going from the blue part of the spectrum, 300 nanometers, all the way through the visible part of the spectrum up to the red part of the spectrum. And there are zillions of lines everywhere. Some of these bands, like in here, are due to the atmosphere. This is a water band absorption from the Earth's atmosphere. And there are a few of these around. They're marked terrestrial H2O bands. But the vast majority of the lines that you see there are from elements in the sun itself. So the sun is 4.57 billion years old. And at the time of its formation, there was a cloud of gas that collapsed. And that cloud of gas preserves elemental abundances in different proportions. And you can see something like, I think at last count, I think I read that you can see 82 elements, unique elements in the sun, which is extraordinary. In principle, you might find even more. And there are also isotopes that you can detect as well. So what we want to do is tap into that information with a high resolution spectrograph and do this for millions of stars. So that was achieved with this mission, the Galar survey, using the Hermes spectrograph. If you've never been, you should go one day. The Warren Bungles is, well, actually you can't at the moment. I was told by the head of the observatory when our provost wanted to go and visit there that you can't go inside and have a look at the moment because of the COVID situation. But in future months, when this is all, we're free of this, hopefully you can have a trip up to the mountaintop at Warren Bungles, which is near Quinnipiac, and see this for yourself. It's really spectacular. So we have this instrument which we can look at 400 stars at once. These are fibers going up to little prisms. So the light from the universe hits this plate, and these fibers are lined up with a star field. So you end up with 400 spectra at a time for 400 stars. And we do this over and over again, and we're up to already over 500,000 stars. So there are many surveys around the world that are focused on stars. The first line that you see there, 2-mass SDSS, these are concerned largely with photometry, measuring the light from stars in different bands. The next one is spectroscopic, looking at the spectra of stars, and Galar is one of those projects. The third line, Kepler K2 test Plato, that's the astrometry missions I mentioned a moment ago. And the last one, Hipparcos and Gaia, Kepler K2 test Plato, these are Astro Seismology, looking at how stars flicker. And the last one, Hipparcos, Gaia, and so forth. This is astrometry, as I mentioned in the previous slides. So it looks a bit squashed. I had to squeeze them in so I could show you more. So it's a very a wonderful team, the Galar team that work on this project. And these are Australians, a few from overseas, mostly Australians working in this country, but some from overseas. who are very actively engaged in taking these data and turning them into science. So one of the questions that we'd love to answer is the following one: where do the elements come from? So this is the element table. As I mentioned before, it's a snapshot in time. If you took this snapshot back at the Big Bang, shortly after the Big Bang, you'd have loads of hydrogen and helium, trace elements of lithium, beryllium, boron, maybe tiny amounts, I should say, deuterium and tritium, and so forth, and nothing else. Then the first stars form and you get CNO and beyond. And then exotic events come along later and create some of these, what are called S-process elements. And then there's a general buildup of what are called the R-process elements, radioactive elements, and so on. So where these elements come from, you know, what were the nature of these exotic sources that form these elements is a very big field at the present time. So what you need to do is measure the strength of these elemental abundances in stars of different ages and try to slice the element table in cosmic time and see what the relative ratios of elements were going back in cosmic time. So you have millions upon millions of lever arms. Like if you're comparing aluminium, say, to lead, or bismuth to ruthenium or cobalt or nickel or whatever. So you can imagine the number of lever arms you have here is enormous. I mean, there is a lot of coupling going on. A lot of elements are formed together and have ratios that don't give you extra information because they form with exact relative ratios. But as I say, there are literally thousands and thousands of lever arms that we could measure in principle. So here are some review papers that talk about how this information is being used to essentially slice through cosmic time over billions of years. So what were the first stars? We do some work in this field, but most of this work is done at the ANU at the present time. And they're having a tremendous run at the moment. They have a Nature paper coming out this year and hopefully at the end of the year, where they claim now to see the signature of the first stars forming black holes. Because in particular, what happens is a supernova, when it explodes, you have basically element buildup, shells, the lighter elements on the outside, the heavier elements on the inside. And the heaviest elements, some proportion of them fall back on the black hole. This is called the Fullback Model by Podolsky at Oxford, which has been developed by the Japanese over the last 20 or so years. And they're claiming to see that signature, that these elements at this end all die off rapidly in the way that was predicted from these black hole models. So, so essentially, there is now a developing belief that the first stars were unique to their time. They were so truly massive, maybe up to 1,000 times the mass of our sun. And they all essentially formed these primordial black holes, these internal black holes, which were able to absorb some fraction of the heavier elements. So the existence of black holes has affected the element table that we see today. So this is something that we are trying to contribute to. I have time coming up on the, well, I had time coming up on the VLT until they closed down operations to look at this in more detail. But we're trying to understand whether the roll-off of the heaviest elements is consistent with the idea of the presence of the first black holes, which is an amazing insight. 10 years ago, I wouldn't have thought that would be possible to do. But there's been real progress in this general area. So what were these stars that created the elements? There's ordinary supernova models, hydrogen, helium, you know, burning to helium, to carbon, neon, and so forth. You've seen this in your classes. You get these shells of metals. Then when they blow up, you get certain elements given back to the universe. Or it might be this pair instability supernova idea where you have this gamma-ray, positron, electron effect at the center, and the whole thing blows up and all the elements get given back. There's no fallback to black holes whatsoever. So there are loads of exotic models explaining where the elements come from. And these are the things that we want to test with our data. But where you look, that's a real problem. Frankly, we don't know where to look for these ancient stars. They may not be metal poor in the sense of having a low fraction of iron. Some of the ones with low fractions of iron will be ancient stars because iron builds up over cosmic time. But there's very strong belief that some of the most ancient stars are metal rich, even more metal rich than the sun, because they formed in the center of this developing galaxy where the star formation rates were ticking over all the time and you were getting up to solar metallicity very quickly, which we see in high rich quasars. So it's not just a case of looking for the most metal poor stars. The question is looking for stars with unique signatures. And it could be that in the future, when we have really good adaptive optics systems going, that when we look at stars right near the black hole in the center, that we will find the oldest stars of all, not at metal poor, but more metal enriched, much more metal enriched. So that's really exciting, and I would like to be a part of that story, trying to figure out which stars in the galactic center might have these ancient signatures. Another approach, of course, is not to observe, but to run models, basically to run cosmological models of how the universe evolved, how dark matter collapsed and took gas with it, formed stars. And this is a very big field these days. There are many groups around the world running these massive supercomputer simulations. It's problematic. Every time they announce they've got the latest models of the latest results, then they end up apologizing and admitting they've made some sort of fundamental errors in the simulations. So it's a constant cycle. The fire team recently realized that there were prescriptions they were using that weren't correct. So I think a lot of these models will be redone. So it's a constant process of trying to understand how well your models track the universal evolution and how well you're using data, how to understand observations as well. So it's sort of a circular loop, but it's a very rich field to be in. If you were wondering what field is guaranteed to carry you decades into the future, working with cosmological simulations and comparing to observations is a very rich field. And we do quite a lot of that here at the University of Sydney. So let me just, to keep to time, I'm going to go past this now. Let me just maybe show this snapshot. This is from a simulation. And the red clumps there are what make the Milky Way. And at a redshift of 5, what it shows you is the Milky Way wasn't even assembled. It was essentially a bunch of clumps about the mass of a dwarf galaxy. And then these all fell together. Several hundreds of these fell together to form the Milky Way. In fact, the next picture shows where those red clumps end up. It's the red light you see in that simulation of the Milky Way. So when you look in the high redshift universe, you are quite limited. You might imagine, well, we're going to go way back to redshift of 10, redshift of 20, let's say, and build it all from what we see with the James Webb. Well, it's actually very, very hard, because simulations predict the Milky Way was a complete mess when you get to redshift 5. And we're already observing at redshift 5 with the Hubble, for example. Trying to track the Milky Way is much more difficult than looking for a thing. It's a bunch of things, an ensemble of things. Anyway, I'm going to move past this now in the interest of time. So galactic seismology, how does the Milky Way ring? This is new work going on at the University of Sydney. We started a couple of years ago and had some papers on this, but I think our work has gone through a revolution with the advent of new, longer, bigger simulations and looking at this at high resolution in more detail. So I've just forgotten her name, but a colleague of mine back in 2010, 2011, first announced that she had evidence for waves crossing the Milky Way disk. And then a number of groups around the world were able to say that they saw some evidence for these ripples, but they weren't sure. They saw bits of it, like maybe a bit of it here or a bit of it there. They weren't sure if they were seeing spiral arms or they were seeing bits of galaxy or whatever. But I want to say now, based on what we know from the Easter Gaia mission, Teresa Antoja's work, that we definitely are seeing waves. So this was a cartoon sketch that was made at the time, which inspired me and Torsten in particular to keep looking in the Milky Way and at the data and to do more models. And this sketch was made by one of the American teams saying, I wonder if these ripples are in fact somehow related to the spiral arms and spiral into the Milky Way. They didn't really have evidence of that. And so we've looked at this problem now with new simulations to understand exactly how does the galaxy ring when it's hit by something very, very massive, punching through the disk. So Lawrence Woodrow in Canada, and Matt Checkers and Lawrence Woodrow in a more recent paper, they put together analytic models, essentially, looking at how disks vibrate. These disks are not solid objects like a discus in athletics or a cymbal in an orchestra. These are actually differentially rotating, as if you're watching water going in a plug hole. So you have to ask, how do vibrations set up in a differentially rotating fluid? That's not as obvious. But they tried to do that, and they found that there were natural modes of oscillation, m equals 0, m equals 1, m equals 2, m equals 3, and they look rather complex. What I'm showing you here is delta Z, basically changes in the height above and below the plane of this synthetic galaxy. So red is shifted towards you and blue is shifted away from you, I think, it doesn't really matter. And this idea goes back all through literature. Alice Quillen, a colleague of mine who works with the Galar team, has done this kind of work in the past. But I think the Chequers and Woodrow in particular, has done a very good job of turning it into something which is much more systematic, the methods at least. This is something that we're tapping into with our work. He calls it Galactic Seismology as a parallel to Astro Seismology, but we've been calling it Galactic Seismology. I don't know, it doesn't really matter. Now, anyway, one thing he did show, which I thought was rather beautiful, and it picks up on work by Dericki and Boulos, is how these modes tell you about the nature of, say, dark matter. The top one is spontaneous modes that come from the disk exciting itself, in the sense that you've got a boundary condition, you've got an edge here. So what do you do at the edge? Do you allow waves to project, to reflect? Do you allow waves to be absorbed? Impedance, like an electrical circuit, for example. You know, you can be artificial with your boundary condition and absorb that mode, or you can let it bounce. So that's a real issue, you know, how you treat, and the center, how do you treat the center? Do you let it go towards the cusp at the center, the black hole, or do you say it gets absorbed there? So anyway, there are lots of mathematical issues that I want to explore in the years ahead. But this is what it looks like if you allow the dark matter or satellites in the halo to punch the disk. They're coming through in clumps, unseen clumps, or even the seen dwarf galaxies. You get different modal patterns, and you even see the disk going up on one side, down on the other side. This is more than just a warp. This is actually a mode, a low-order mode that basically ripples around the disk. So you can see where galactic seismology begins to say some very interesting things about how the disk is ringing and how it's interacting with its environment. So let me very quickly show you these recent simulations. So Archil, how am I doing for time?
You're doing well. Maybe another 5 minutes.
Okay, good.
That's discussions.
Yeah, that's all good. Right. So, so this is one of Torsten's simulations, where this is already a major achievement. You won't believe it, but it is, because for many years, when you ran these simulations of disks rotating, they generate structure because of noise in the simulations, not real noise. I mean, noise because of numerical noise. And what you'd see is that when from the side, the disk would start to heat up over cosmic time. So Torsten can now run this for 4 billion years, and it shows no structure, which is really a remarkable achievement to do with new developments in coding. Now, that same simulation was now run again over 1 billion years and hit with an impactor. Did you see that little white thing go by? Let me run that one more time. And now what you see are you see basically density waves and bending modes, ripples in the disk evolving as a consequence of that impact. So remarkably, we've been able to fit those evolving density waves with a very simple model. And here's, I have to put my glasses on now to read this, 190, 285, all the way up to about 1 billion years. And that same model with the simple time dependence, early on it doesn't match because the disk is settling down, but later on it does. You see that the later time frames after 500 million years do settle down, and it tracks the model really, really well. So it's unsettled, then it becomes settled. So we have a sort of a theoretical model for how the simulation is working, and we can use that to apply to the Milky Way, which is really nice and was actually unexpected. I think we're the first ones to see what's called a Lindblad resonance evolve in time, as has been described in theory in a simulation. Now, you don't just have the effect of the spiral arms density waves winding up, you also have bending modes waving. Remember these waves that propagate across the disk? They're not like ripples in a pond, they actually wrap up like spiral arms, but they're not spiral arms. They're quite separate from the spirality you see in these pictures. So this is an example. So you start with a cos 2 theta dependence. That might be white might be moving upwards, black might be moving downwards, and then as time passes, you see it wrap up from the inside out because of differential shear. And you see that bending mode now, that bending mode, we see that also in the simulation. We think we see the same thing in the Milky Way, in fact. And this is what you see if you present it as a velocity field. Red is red shifted, blue is blue shifted, so it's going up and down in velocity. You can do it also in distance. And it's wrapping up as time goes by. Now, if you put this together, this is the first time it's ever been done. This is new work from the both of us. So the spiral arm wrapping up is the black lines, and you see how it changes with time, going from time frame to time frame. You see how it wraps up more and more and more. And the red is the bending mode, is the wrapping up of that of the up-down corrugation, the ripples on the pond, imagine you had ripples in a pond that got caught in going down a plug hole, for example. You might get something like this. So basically, this is what we would say is what we're seeing in the simulations. We think we're seeing it in the Milky Way. We want to demonstrate how it's happening in the Milky Way. So this is really what I mean by galactic seismology. So I'm going to go past this now and go to my concluding slide. In the interest of time, I'm not going to mention any of this, but we do work on things like how does gas enter the Milky Way, which is a very nice field. We have a Nature paper coming out in 2 weeks describing how gas is coming in a new way into the galaxy through the dwarf galaxies. They have these very massive hot halos that fall in with the dwarf galaxies. That's coming out in 2 weeks. We've actually done a projection on the sky to show you what that might look like. Also, a lot of my work in the recent years has been on the black hole at the galactic center. This is undergoing these extraordinary explosions over billions of years. This is what I discovered in 2003. This is, you can see sort of this is the galactic center of the Milky Way plane. It's a beautiful hourglass, wine glass effect above and below the plane. This is from an explosion above and below the plane from the black hole. And then remarkably, it was seen in gamma rays by the NASA Fermi satellite in 2010, 7 years later, but in gamma rays, the first time any explosion had been seen in gamma rays in a galaxy. So that had lots of media attention. You might remember last October, there were lots of stories on the web, and I even got stuck next to Donald Trump on one website, which was interesting. And that is also work that we are doing. We have sorry, I had a little, I can't find it now, but here it is. So basically, just to show you, there's the jet coming out of the center of the galaxy, the explosion. These jets, doesn't matter what direction they go off in, they can go off at 45 degrees, they can even go off in the plane. They generate these giant bubbles of hot gas that come out. So you can see a trend here. Everything that we work with, we don't just work with the data. We also work with complex models. Very good. So let me just finish up with one final statement. This work doesn't finish anytime soon. There are always new facilities coming online. One of those is the Giant Magellan Telescope. University of Sydney is very much involved in that, hopefully with the instrumentation as well as the science. Australia is a part of that, and that'll give us a 25-meter telescope to look at even further into space, to look at even fainter stars. So everyone watching this is all about you, not me. I'll be long gone. They'll put me in a, I don't know, they'll put me in a chair by the beach somewhere, and you'll all be doing this work for yourselves years into the future. Not just that, but you've also got the Gaia satellite is having future releases. There's other satellites like WFIRST happening as well. Sorry, I lost my, here we are. You've got these new astrometry satellites like Plato. You've got the James Webb going up in hopefully within a few years. And as exciting as any of them is the European ELT. We're hoping to get full ESO membership in a couple of years, and that would give us access to this truly huge monster, 40-meter mirror, amazing project. So, and then I think finally, what I want to say is this: we're looking for a narrative for the Big Bang to the present time, and really, it's all about dark matter. It's about dark matter substructure evolving over billions of years. And dark matter is what's driving everything. And it's no different for the Milky Way. The gas is a very complex, dark matter is somewhat simpler if you treat it as gravitational clumps, but truly we don't know what it is. But the gas part of it is very complicated. Like how do you track gas physics over billions of years? We're nowhere near doing that properly. But anyway, that's what we're after, is a narrative for where the Milky Way came from. Thank you.
Thank you very much, Jos, for very informative and interesting talk. And I'm sure there will be questions now. So I encourage first students to ask questions, either via chat or just unmute your mic and ask questions.
You can ask anything you like. Students who've been through classes with me know I'll answer anything, absolutely anything. Is there a chat window?
Yes, I'm looking at.
That hasn't been used.
All right, maybe I'll ask first question,
yeah.
Jos. I'm really working on a model of charged black holes. Actually, it's more theoretical model, but will be interesting to look at the manifestations of course charged black holes. You know that according to No-Hair theorem, the black hole can manifest mass, obviously spin, and the charge, and that's it. And of course, the people believe that astronomical black holes are not charged. But suppose you have a charge in a black hole in the galactic center. What type of observation you can have? I thought that for example, size of the black hole can modify, and I read the decade-old data that size is more consistent with a charged black hole rather than the Schwarzschild black hole having there. Do you have any comments about that?
Let me ask you a question. Can your charged black hole rotate?
Yes, of course, it can rotate as well.
No, but can it rotate relativistically?
Yes, in principle, yes, but I don't think this huge black hole will rotate relativistically. Is that?
I think you'll find that all black holes rotate at very high speed.
Right.
And if you believe what's been claimed about them, so I mentioned before about those stars going into the galactic center, there's also evidence of gas emission, periodic gas emission. If you believe what the German groups are saying, it's sort of every 17 minutes. That's well inside of the last stable, the ISCO, the last stable orbit. And the only way it can be true is if it's rotating the black hole is rotating at very high speed. I don't know what the number is. People have said 0.2 C or something. I don't know. I don't know what the answer is at the moment, but there are claims that you're seeing periodicity in the emissions from the inner accretion disk, which are way above the black hole being static, and it's rotating. So my sense is that the Event Horizon Telescope will, within a few years, give us maps of the shadow of the background light source. So essentially, that'll tell us something about the true scale of the event horizon. Okay, so if you're saying a charged black hole could exist at any speed of rotation, can the charged black hole interact with particles?
Well, the charged black hole obviously produces. Oh, sorry. It's obviously produce. It depends how big is the charge, obviously, but it produces all sorts of electromagnetic interactions, right?
What you really want to see is Hawking radiation, don't you? But you're never going to see that.
No, not Hawking radiation. It's electromagnetic radiation, essentially. But what I was thinking of is how we can distinguish this with all sort of violent processes which are going on, in plasma around the black hole. So I was thinking that it also modifies the size of the shadow. You can predict the different size, whether it is charged or not. And if it carries the charge, I think the shadow size is typically smaller for the usual uncharged black hole. So I was thinking whether you can distinguish, to measure accurately the size of the black hole to distinguish that.
Well, it comes from variability, doesn't it? If you see variability, the idea is that it would be incoherent if it's if the timing suggests a smaller physical scale. It can't be going on a larger physical scale because the front and back, well, it depends really on your geometry. Mm-hmm. I think the Event Horizon Telescope shadow will be your best constraint, won't it?
Yes, I hope so, yes. But it's interesting.
They haven't announced their result. It's a much more difficult measurement than M87. But I know they're onto it. It's like the Holy Grail.
I looked the paper. I don't remember now the others. The decade ago when they have a measurement of the galactic center size, and of course the measurements are not that accurate. And what they claimed at that time that the charged black hole is better fit than this uncharged black hole. But I don't know what the situation now.
Well, I can't see. I don't understand how a charged black hole interacts with its environment.
Well, it's basically, the shadow. It's a geometry which is changing because you have extra interaction due to the charge potential besides the gravitational potential, and so it changes the the photosphere and things like that, and eventually the size of shadow you can show that it's smaller.
Oh, I can see how that might work. Yeah. But I think the Event Horizon Telescope, the first image we're going to get, if you want to call it an image, won't be very good. But if you believe what the upgrades will give you, look, it's going to be more impressive in the future. I mean, if you look at M87, that wouldn't be good enough for you now to tell me whether M87 has a charged black hole, is it? But I mean, you could. So you need to. So I think you need to scale your result based on M87's shadow.
Yeah, well, I mean, it's yes. We look at that. It's almost very consistent with a zero charge. So
yeah.
Okay.
Yeah, it's fantastic. I mean, but to your insinuation, I think the Galactic Center supermassive black hole is the future proof of astrophysics. I think we'll be doing this for even longer than we're studying, searching for extraplanetary light, biosignatures and so forth. And in fact, both of them, looking for extraplanetary, extrasolar, what am I saying? Extrasolar planets, the atmospheres, biosignatures, and the black hole at the Galactic Center. I think both of those future-proof astrophysics.
Yeah, interesting. So
we'll be doing it forever.
So do we have other questions or points of discussion you want to raise?
Yeah, can I ask quickly about this phase spiral? I'm pretty intrigued as to how far away we are from understanding the cause of this. I mean, is Gaia good enough that you can start to, based on your model, constrain when this impact should have happened, like the mass of the dwarf or whatever produced it was, or are we going to need something kind of beyond Gaia to be able to, have more wraps in the phase spiral to actually be able to constrain that?
So if you look at my 2019 paper with the Gaia team, it's a very long paper, and we go through and make predictions about what you would see around the Milky Way based on a simple impact scenario. It turns out the Chinese Lamos telescope claimed to see the phase spiral further away from us in various directions, going around in azimuth or in radius. They claim to see it over a larger extent, which may be right. Data is not quite good enough to really test our model, I would say. However, the new work that I've been doing, finishing up with Torsten, suggests that it's much more nuanced than saying it's here and it's there. In actual fact, it's where it exists and how it comes and goes matters. It's like a resonance of anything. Like if you were to hit a drum skin and see how vibrations go around the drum skin, the idea that it should be everywhere at once, I think now is not true. So if you believe the galactic seismology models that we're producing, which are certainly the best ones ever produced, but if you believe they represent real galaxies, I would say that they suggest that you will not see it everywhere. And the way that you do see it moving around, the phase spiral moving around the galaxy, will tell you a great deal about the timing and where and when. If you do see it everywhere and it looks the same everywhere, I think you haven't got information about when things happened and how they happened. But if you don't see it everywhere, if it really is regional, it comes and goes, much like anything which oscillates, then I think you do have a lever arm to unravel where it all happened and how it happened and when it happened. So I think with Gaia DR3, the big release of Gaia, which was going to be the end of this year, has now been moved to the end of next year, maybe. I don't know if it's a year or more. Whenever the Gaia releases the big DR3, I think that data will be good enough to really test how far the phase spiral goes. Is it as smooth as it looks in these papers, or is it much more variable? Does the phase spiral change phase as you move around in azimuth, in radius, and so on? So I think the new models suggest that the Gaia DR3 release will tell us yes or no to your question.
But is the interpretation that this was due to some kind of impact? Is this a consensus now, or is there still?
Oh, yeah. The consensus would be that there are definitely other models. People talk about the galactic bar, the bar in the middle of our galaxy, bucking like a rocking horse, and the bucking motion, which you do sometimes see in simulations, often not very good simulations where you've got instability in the simulation. And they're claiming that the bar is doing this and that creates waves. It's Kopperskov's paper. I don't think that's correct, because the bar in the galactic center, like the galactic plane, is very, very flat at the center. They're very aligned. You don't see tilt of the central bar. And there are other ideas out there. But by far the most generic is the idea of a strong impulse bashing the disk, causing the disk to ring like ripples in a pond.
And is Sagittarius still consistent with that, or could
yeah, yeah. Oh, it's consistent as good as the models are. You know, yeah. So I'm on about at low level. Everyone would agree that Sag can drive these ripples and waves. Yeah, but what we're showing, it goes way beyond that. It doesn't just drive ripples; it also drives the spiral arms, in the density waves in the disk, and these couple together in a very complex way, and that's what's causing the phase spiral. So we haven't finished that work yet. We're close to finishing it. I think it has to be an impulse. I think it would be very hard to explain with anything else. The other models all have fundamental flaws attached to them. They still get published.
Okay, are there any other questions to Joss?
So if there are students online who are too shy to ask me questions, which is surprising, given my class, you will ask me whatever you want, just email me offline, whatever. You know, as always, any question is fine about anything. It went by in a bit of a rush, so there's no reason why you should understand any of it.
All right. I don't see any other questions, Joss. So thank you very much for very clear talk again. And we'll presumably finish today's discussion on that.
Okay, great. So as I say, anyone that's been listening to this, they're very welcome to ask me anything they like. And it can just be a private conversation about particular parts of this work.
All right.
Okay, thank you very much.
Yeah, thanks. Thanks, Joss. Thanks, everyone.
All the best.